given bounds for some functions, we can create kind of a bounding box for an area, and then we can use calculus to determine the area of the region that we just bounded. So we have these constraints. We know that y is it's 16 minus x squared, x is 0, x equals 3, and y equals 0. So all three of these are straight lines. These are vertical lines. That's a horizontal line. And this is a curve. So what we want to do is draw all of these together and figure out what region we're talking about, and then set up an integral that makes sense to compute the area of that region. So x equals 0 is this line here. X equals 3 is this line here. Ooh, that's not a very good line, but just pretend it is. Y equals 0 is this line here. So we already know that we're somewhere between this strip and above that strip. So because we're bounded between there and we're bounded above there. So 16 minus x squared. Well, that looks like this. It also goes out this way too, but that's pretty poor parabola, but that means it's got to be bounded above there. Right? That would be, because it can't go below y equals 0, can't go above y equals 16 minus x squared, and then goes from 0 to 3. So those are kind of our constraints. Well, if that's true, then what we do is we say, all right, the difference in this area, or the height at any given point, is this curve minus 0. So that tells me that the integral I'm going to set up, the height at any given point is this height minus 0. So I could say that's the height. Now, so the integrand, that little piece there, is generally you could think of that in terms of area. That's your height, and then the width is going to be how far in the x direction do you go, and where do you start, where do you end? We start when x is 0, and we end when x is 3. So why am I doing all that? Well, I could, and I'm not going to for this, but you could have said, okay, well, what if I wanted to bound the same thing, but instead of y equals 0, what if it was y is equal to let's see, let me just think about this for a second. 2x. If y was equal to 2x, right, then just making sure that this all comes out, then that means that the height would have been like that line. So instead of it being 0 here, it would have been like that 2x there. And that would have been a separate integral, but that's how you do it. You say, what are my height at any given point? And then the width goes there. So, but we're not going to do that red part. That's not going to be what we do right now, but that's just kind of a taste of what you could do. Anyway. Oh, no. Sorry, I want to keep the blue. All right, so that is the integral from 0 to 3 of 16 minus x squared dx, which then is, the antiderivative is 16x minus 1/3 x cubed from 0 to 3. So then I plug in 3, I get 16, 3 minus 1/3 3 cubed minus 16 times 0 minus 1/3 0 cubed. From there, I say that's 48 minus 9, because 3 cubed is 27, divided by 3 is 9. And then those are just 0. So it looks like the area is 39. And that's really how you do it. It's really not any more complicated than that. You just have to construct your bounds on your region, determine what's kind of the top and what's the bottom, and then plug that in. Now, if I wanted to do that with 2x, for instance, the same exact problem, I would the easiest way to do that is to instead set it up like this, right? Because this is the same thing, I just split up the integrals. Why did I do that? Well, I already know what this is. This is 39. And so then if I do this here, that's x squared from 0 to 3, which is 30. So, which is what you'd expect, right? If I shave that little piece off, I'm going to get a smaller area. But there's no real difference there. It's just a little more complicated because you don't have a horizontal line here. You have something that's, you just have a changing height over time.